The classic image of a child bouncing off the walls after eating candy, only to crash into fatigue or irritability a short while later, has long puzzled parents and scientists alike. While much of this sugar high lore has been dismissed as myth in controlled laboratory studies, real-world observations suggest there may be more to the story than placebo or parental perception. A compelling, underexplored mechanism could lie in the dynamics of brain glycogen, an often overlooked form of stored energy that plays a vital role in fueling neural activity, particularly during developmental stages. In children, the brain is an energy-demanding organ, consuming roughly half of the body's available glucose at rest. To buffer against fluctuating blood sugar levels and support bursts of neural activity, like learning, play, and emotional regulation, the brain relies on astrocytes, glial cells that store glucose in the form of glycogen. This reserve acts as a short-term energy bank, supplying fuel to neurons during periods of high demand or when glucose supply from the bloodstream is insufficient. But this system, especially in young, still developing brains, may be particularly sensitive to large and rapid changes in circulating glucose levels. When a child consumes a high-sugar food or drink, blood glucose spikes rapidly. This surge leads to a rush of insulin secretion to manage the excess glucose, promoting uptake into muscles, fat, and brain cells. In the brain, glucose is taken up both for immediate use and for conversion into glycogen, primarily by astrocytes. The initial spike in glucose availability temporarily increases neuronal excitability, potentially enhancing alertness, impulsivity, or hyperactivity. For a brief window, the brain may be flooded with energy, especially in areas tied to reward, attention, and motor control, helping explain the sudden behavioral stimulation often associated with sugar intake. However, the rapid rise in insulin can also set the stage for an abrupt drop in blood glucose, what's sometimes called rebound hypoglycemia. In this low-sugar state, the brain attempts to compensate by mobilizing its glycogen reserves. Yet in children, the mechanisms for glycogen breakdown and glucose shuttling between astrocytes and neurons may not be as efficient or stable as in adults. As a result, neurons may experience temporary energy deficits, particularly in regions responsible for sustained attention, emotional regulation, and impulse control, areas already under development in young brains. This could partly explain the post-sugar crash some children experience, marked by fatigue, mood swings, irritability, or inattentiveness. If glycogen stores were excessively depleted in response to the initial sugar spike, or if mobilization was too slow to meet neuronal needs during the rebound phase, the brain would be left in a temporary state of metabolic imbalance. In essence, the sugar high and subsequent crash may be two sides of the same glycogen-driven coin. First, excessive stimulation from rapid glucose influx, followed by compensatory depletion or mismanagement of energy reserves. Adding to this complexity is the role of cortisol and stress hormones, which can be triggered by both excitement and metabolic instability. Cortisol influences glycogen storage and glucose availability in the brain. If blood sugar swings are frequent, this hormonal system may become overactive, contributing to an environment of chronic low-grade stress that further destabilizes energy metabolism and cognitive emotional performance in children. It's important to emphasize that not all sugar consumption leads to this roller coaster effect. The type, context, and composition of the meal matter greatly. Natural sugars found in whole fruits, for instance, are absorbed more gradually due to the presence of fiber, vitamins, and polyphenol, leading to a gentler glucose curve and more stable glycogen dynamics. In contrast, refined sugars in sweetened beverages or candy, lacking buffering nutrients, hit the system rapidly and forcefully, overwhelming regulatory mechanisms. Frequent exposure to such sugar spikes may train the brain's energy systems into a pattern of volatility, which over time could influence behavior and even brain development. What's still uncertain, but deserving of further research, is whether repeated cycles of sugar-induced glycogen mobilization and depletion could have lasting effects on cognitive development. Preliminary animal studies suggest that early-life dietary patterns can influence astrocyte function, insulin sensitivity, and neuroinflammation, all of which may shape long-term brain plasticity and vulnerability to conditions like ADHD or learning difficulties. While causality is not established, the associations are strong enough to merit deeper exploration, particularly in children with pre-existing attention or behavioral challenges. In conclusion, the sugar high and its often followed cognitive crash may not be a myth after all, but a complex interplay of rapid glucose metabolism, brain glycogen fluctuations, and immature regulatory systems in children. While occasional sugar consumption is not inherently harmful, frequent spikes from ultra-processed sweets may strain the brain's energy balance, contributing to mood shifts, focus difficulties, and long-term metabolic imprinting. Understanding how brain glycogen mediates these responses could not only validate parental observations, but also refine dietary guidance for supporting stable, healthy cognitive development in children.